Hello students, in this video we're going to use elementary row operations to compute the inverse of the matrix A. Now I wrote the identity matrix, the 3 by 3 identity matrix, that's the matrix with just ones on the diagonal, zeros elsewhere, because it plays a prominent role in solving systems of equations when using the matrix inverse, and also the whole point oftentimes of finding the inverse of a matrix. It's oftentimes because you want to multiply it by the matrix itself to arrive at this identity matrix. Okay, so let's proceed. What I'm going to do is first notice that if I multiply A by the identity matrix, I get A back again. In fact, if I multiply the identity matrix times A, I get A back again. So this is one of the cases where you can multiply in either order. A times A or I times A gives you the matrix A. You could just, you could just check that. If you take this vector, so if you just take 1 and you multiply it by this column here, you end up taking 1 and multiplying it by this column here, and then taking 1 and multiplying it by this column here. When you add them all together, you ended up just getting this column back again, this column, middle column back again, and this third column back again. Adding them all together, of course, gives you the matrix A back again. All the zeros will take care of the fact that this column will remain intact, this middle column will remain intact, and this third column will remain intact. So ultimately, as I said before, we want to get to the case where we have A times A inverse is equal to the identity matrix, and A inverse times A is equal to the identity matrix. Okay, now let's figure out how to compute A inverse. Now, what we really are going to do is we're going to figure out a way to come up with a column vector so that when we multiply by the matrix, we get this entry of the identity matrix so that we can satisfy this top equation here. Functionally, the way that most people interpret this or think of this is you put the identity matrix on the right-hand side of this augmented matrix, and then you perform elementary row operations to the left-hand side to make the left-hand side look like the identity matrix. And then the result, the matrix on the right-hand side is the inverse matrix. But keep in mind, really what's going on here is you're solving 3 different linear systems of equations at once. This first column is one right-hand side, this middle column is another right-hand side, another case of a right-hand side, and this third column is another case of a right-hand side. And you're determining the row operations you need, which will give you the solution vector for each of these cases that give you these respective columns. So in other words, that's how you're going to construct A inverse. Okay, but we'll just consider this as functionally what's going on here, and that is we're going to try to turn this left hand side here of this augmented matrix into the identity matrix. So in order to do that, I have to eliminate the 2's below this. I'm going to use this top one here as my pivot, and I'm going to convert these 2's here to zeros. In order to do that, I'm going to perform the operations of row 2 minus 2 row 1. I'm going to replace row 2, and then row 3 minus 2 row 1. I'm going to replace row 3. When I do that, I get the following result. And notice that I perform it on the right-hand side as well. So minus 2 times the top row gives us a minus 2 in this entry here and a minus 2 in this entry here. Then I want to get rid of this minus 3. So I'm going to multiply row 2 by minus 3/5, add it to row 3, and then replace row 3. When I do that, I get the following result. Now, again, I have to do these operations to the right-hand side as well. Now I'm going to clear out those 5's in the denominators because I don't want to deal with those fractions. So I multiply row 3 by 5. And then that's pretty easy to see. So I'm just going to kind of jump to the next operation. So now that I have the matrix in upper triangular form here on the left-hand side, I'm going to start working upward, and I'm going to try to put this matrix on the left into row reduced echelon form, the RREF, which is going to actually get us to the identity matrix on the left-hand side. Anyhow, what I need to do is I need to eliminate this minus 2 and I need to eliminate this 1. So I'm going to add 2 times row 3 plus row 2. And when I do that, I get a 0 minus 5, 0, and then a minus 10, right? Because 8 minus 8 minus 2 gives us minus 10. Minus 3 minus 2 gives us minus 5. And 2 times 5 gives us a 10. And then likewise, I'm just going to take R1 minus R3 to get rid of this 1 and replace row 1 with that result. And that's what you get, okay? And notice that the 1 and 5 remained intact here. So I'm almost to a diagonal matrix here on the left-hand side, just a couple steps away. So what I'm going to do is I'm going to take row 2. I need to eliminate this 5 up here. So I'm going to take row 1 plus row 2, and I'm going to replace row 1 with that result. So this should be a row 1, not a row 2. And when I do that, I get 1, 0, 0 on the top. Notice I have 0, 0, 1 on the bottom row here, so I'm almost to the point where I have the identity matrix here on the left-hand side. When we just add row 1 plus row 2, we see that we get minus 5, 2, minus 2, 5. And then finally, I'm going to divide row 2 by minus 5, or I'm going to multiply row 2 by minus 1/5. And when we do so, we get the identity matrix on the left-hand side. And here is on the right-hand side is our result of performing all these elementary row operations. So in other words, this first column vector here is the solution to the system of equations that we have here with the augmented matrix with 1, 0, 0 on the right-hand side. So this is the vector that you have to multiply this matrix by to get 1, 0, 0. This middle column here is the solution to the linear system of equations with 0, 1, 0 on the right-hand side. So that's the vector you have to this is the vector you have to multiply this matrix by to get 0, 1, 0 on the right-hand side. And likewise for the third column, if you wanted to get 0, 0, 1. Stitching these vectors together, we see that we get a matrix, and that gives us the inverse matrix. So if we take A times A inverse, or A inverse times A, this is again one of the cases where matrix multiplication commutes, then you'll see that you will get the identity matrix. And there's value to that in solving a system of equations, and I have a subsequent video where I use the matrix inverse to solve AX equals B, a linear system of equations. All right, good luck.